Hey class, Mr. Bean here. This is going to be video 44. So it's going to be video 44, conservation of energy for AP Physics 1. So video 44, and we're going to be talking about, and this is conservation of energy. So on here it says energy cannot be created or destroyed, it can only be changed. Now that's a very powerful phrase. Now I want to introduce mathematically what this means. Okay, so essentially it means that conservation means the total energy before any interaction has to equal the total energy after the interaction. Okay, so initially what you have here then is that you have potential energy. I'll go ahead and put O here for initial potential energy. Now this could be in a form of gravitational potential energy, or it could be potential energy of a spring. Okay, it can mean both. Okay, and and it's going to be plus any initial kinetic energy minus any work done by friction, okay, equals uh, final potential energy plus the final kinetic energy, okay. And again, this could be a spring, or it could be gravitational. Okay, it doesn't have to be one or the other. It could, it could change from potential gravitation to potential. I mean, to a spring, and spring to gravitational. It all depends on the situation. So this is the main formula that we're going to be using throughout our discussion. Okay, and sometimes when friction is ignored, we just basically leave this out. But I like to go ahead and introduce it just so that you know that it is there. So as we go through this, go ahead and take some time to read through this, look at the worked out example that they have here. Here again, worked out example here, and here's some more stuff here about conservation of energy. Here's a conservation. Now, here's this problem here. They're going to talk to you. Look at this problem right here. Now, there's two ways to do this problem. We can do it through conservation of energy. You can also do it through kinematics. Okay, so take a look at this problem here. An object falls from a height of 10 meters above the ground. Neglecting air resistance, find the velocity the moment before the object strikes the ground. Okay, all right. The conservation of energy approach, basically, here it is worked out, but I'll go ahead and take a look at it here. So potential energy plus kinetic energy initial. Okay, there's no friction, minus work done by friction is equal to final potential energy plus the final kinetic energy. All right, so here it says it's 10 meters above the ground. So this is going to be mg. I'm going to use capital HO to show our initial height. Here's HO, right? Okay, now it says here, okay, so it looks like it doesn't tell us, but we're going to assume it starts from rest. That means the kinetic energy is 0, and we can neglect air resistance. So that's also 0. Now, when it hits the ground, it's going to have no potential energy. Okay, it's going to be 0. Okay, but it will have some kinetic energy, 1/2 mv squared prior to hitting the ground. So looking at this here, we can see that the m's cancel out, so mass is not needed, and we can quickly solve for v here. So v is going to be, if I do this out, it's going to be the square root of 2gho, or in this case, delta y, and you get the same answer here. Okay, now if we go over here to the kinematics approach, we'd have to use, time is not given. Okay, and we have acceleration is 9.8, so time we do not know, so we would use this formula right here, and we would use this equation here and solve it, and we would get 14 meters per second. Okay, personally, I like the conservation of energy better. All right, so let's go ahead and take a look at 5.41, and let's go ahead and kind of see what's going on here. Okay, go ahead and read it. And so the diagram shows a toy cart possessing 16 joules of kinetic energy traveling on a frictionless horizontal surface toward the spring. Okay. All right. If the cart comes to rest after compressing the spring a distance of 1 meter, what is the spring constant? Okay. All right. So I'll set this up for you and let you figure this out. So we have the initial potential energy, okay, plus initial kinetic energy minus any work done by friction is going to equal the final kinetic energy plus the initial kinetic energy, or excuse me, plus the final kinetic energy. All right, so initial kinetic energy is 0. There's no friction, and the final kinetic energy is also going to be 0 because it's going to come to rest. Okay, so we are given the kinetic energy, and this is going to be for a spring. So there's 1/2, right? There's k, the spring constant, and what is it? X squared, right? X squared. All right. So from here, we should be able to solve 5.41. All right. We'll go ahead and hit pause and let you work on it. All right. 5.42. A child does zero point 0.2 joules of work to compress the spring in a pop-up toy. If the mass of the toy is 0.01 kilograms, what is the maximum vertical height that the toy can reach after the spring is released? Okay. All right. So it's compressed. Okay. Then it's popped up. Okay. So let's take a look at the approach here. Okay. Here's the initial potential energy, right? Uh, plus the initial kinetic energy, right? Minus any work done by friction is going to equal what we have here, the final potential energy plus the final kinetic energy. All right, now looking at the problem here, before we start anything, let's figure out what is 0. Okay, so we're going to assume that there's no friction. Okay, so it starts from rest, therefore there's no kinetic energy. It says, what's the maximum vertical height? Well, when it reaches a maximum vertical height, remember here's the spring here, it's released and it shoots up in the air. So when it reaches maximum height, h right here, velocity is 0. So there is no kinetic energy at the end. So essentially what we have is the initial potential energy, which is going to be of the spring, has to equal the final potential energy gravitational, right? So this is going to be 1/2, right? And here's k. And well, actually, we already have the 20.2 joules, so we're already given this value here. So kx squared, okay, this is already given to us, equals mgh. This would be mgh here. So we are given this value right here, and we know the mass of the toy, and we know what g is. So all we need to do now is find h. We'll go ahead and pause and let you go ahead and finish the problem off. All right, 5.43. Okay, a lawyer knocks her folder of mass M off her desk of height delta Y. What is the speed of the folder upon striking the floor? Okay, so again, potential energy initial plus kinetic energy initial minus any work done by friction is equal to potential energy final plus the kinetic energy final. All right, so I'll let you go ahead and work on this and try to solve for speed when it strikes the floor. We'll hit pause. All right, 5.44. A 65 kilogram pole vaulter wishes to vault to a height of 5.5 meters. A, calculate the minimum amount of kinetic energy the vaulter needs to reach this height if air friction is neglected and the vaulting energy is derived from kinetic energy. All right. So in this case here, we'll go ahead, and then B is calculate the speed of the vaulter must attain to have the necessary kinetic energy. All right, so we'll go ahead and break it. We'll do A first here. And so part A, let's go ahead and give you a hint here. So we're going to start with potential energy initial plus kinetic energy initial minus any work done by friction is equal to final potential energy plus final kinetic energy. All right, so take a quick look here and kind of see what kinetic energy needs to be. So, okay, take a look here. So we do need, uh, this is going to be 0. That's going to be 0. This is going to be 0. So it looks like we can find kinetic energy from here. So we have to figure out what is this here. This is gravitational. So from here, we should be able to solve for KO. Then on part B, once I know what the kinetic energy is, I want to solve for velocity or speed. It'll just be 1/2 mv squared. So once I solve for this, I can quickly solve for the speed here. All right, we'll hit pause and let you work on that. All right. 5.53. The work done in accelerating an object along a frictionless horizontal surface is equal to the change in the object's what? Okay. Hit pause, let you answer that. Okay. 5.46. A car initially traveling at 30 meters per second slows uniformly as it skids to a stop after the brakes are applied. Sketch a graph showing the relationship between kinetic energy of the car as it is being brought to a stop and the work done by friction in stopping the car. All right. All right, so kind of help you out here, help you out a little bit. I'll go ahead and help you label the axis here. Okay, so here we're going to have kinetic energy over here, and this will be work done by friction. All right, so kind of like sketch how the graph should go. Okay, I want you to describe it to me, and on Edpuzzle, I'll have a diagram of several looking car or several graphs, and you choose the one that it corresponds to. All right, you hit pause and let you work on that. Okay, 5.47. A 2 kilogram block sliding down a ramp from a height of 3 meters above the ground reaches the ground with a kinetic energy of 50 joules. Total work done by friction on the block as it slides down the ramp is approximately what? Okay, all right, so now we do have some friction involved. Okay, so let's take a look here. We'll have kinetic energy initial plus potential energy initial minus any work done by friction is going to equal the final potential energy plus the final kinetic energy. All right, so here's we're going to do a graph, do a box here. Here's the ramp here, and we'll call this some HO, initial height HO. And it says a block is sliding down here, and it looks like there is some friction. So we're going to draw some little sketches here like this to show there's friction. Okay, and this is mass M here. And it says, what's the total work done by friction on the block as it slides down the ramp? Okay, and we'll call this some distance D here. So the ramp distance is D, right? And we'll call this maybe angle theta here in case we need it. Okay, the total work done by friction. All right, so we'll go ahead and use this formula here. So we want to try to find what this is here. Okay, so sliding down a ramp with 3 meters and reaches the ground with a kinetic energy of 50 joules. Okay, so so down here, so it starts from rest. So down here, there is a final kinetic energy, right? Is given to us as final kinetic energy is 50 joules, right? There's 50 joules here. Okay, and the potential energy final is also going to be 0 joules. Okay, all right. So up here initially, the initial potential energy is going to equal mgho, right? And it has okay. So looks like it starts from rest. So we know that kinetic energy initial is going to be 0. All right, so we need to take a look at this problem here and kind of plug things in here. Some things are 0, and we want to solve for work. All right, and see what the answer ends up being here. Okay. All right, we'll hit pause and let you work on that. Here's 5.48. Okay. Four objects travel down an inclined plane from the same height without slipping. Which will reach the bottom of the incline first? Okay. A baseball rolling down the incline, an unopened soda can rolling down the incline, a physics book sliding down the incline without friction, an empty soup can rolling down the incline. Okay. All right. Now we have not yet talked about rotational motion. Okay. But if something is rolling, okay, so I'll give you a little preview here. Let's say we have a sphere here or a tire. Okay, this is there's a little tire here, and we'll kind of, okay, so we have this tire here, and it's rolling like this. Okay, so total kinetic energy is made up of two parts. There's kinetic energy translational, which is the straight part, plus any rotational kinetic energy. Okay, rotational kinetic energy. So if it's rolling, that energy is being split to translational and rotational. So using this idea here, see which answer here seems most appropriate. Okay, we'll hit pause. Okay, 5.49. As a box is pushed 30 meters across a horizontal floor by a constant force of 25 newtons, the kinetic energy of the box increases by 300 joules. How much total internal energy is produced in this process? Okay, we hit pause. All right, so in this problem here, um, a box is pushed 30 meters across a horizontal floor by a constant horizontal force of 25 newtons. The kinetic energy of the box increases by 300 joules. How much total energy is produced during the entire process? Okay, well, in this case here, we have to use the work energy theorem, okay, which says that work is equal to the force, was it parallel, right? Times any delta x. All right, so in this case here, we do have 30 meters and we have 25 newtons, and it's being pushed horizontally. Okay, so using this here, we can figure out what this answer here is real quick. And I'll let you figure this out, and we'll go from there. We'll hit pause. Okay, 5.50. Here we have this, go ahead and read the problem here. And we have this, we'll kind of put this like right here, like so. All right. A mass M sits on a frictionless surface and is attached by a light string across a frictionless pulley to mass M2 as shown below here. What happens to the gravitational potential energy and kinetic energy of M1 and M2 when M2 is released? All right. So take a quick look there and see, kind of just think about what happens here. So this thing begins to move here. Okay. What happens to the gravitational potential energy, and what happens to the kinetic energy here and here? Both. Okay. So what happens to the kinetic energy here and the gravitational potential energy? And same thing here. What happens to the kinetic energy and the gravitational potential energy? What happens in both cases here? Okay, go ahead and hit pause. All right, 5.51. A box of mass M is attached to a spring with a spring constant K and sits on a frictional horizontal surface. Okay, so here's this frictionless horizontal surface. The spring is compressed a distance x from its equilibrium position and released. Determine the speed of the box when the spring returns to the equilibrium position. Okay, all right, so kind of frictionless, so it's kind of help you out here. So we have potential energy initial, okay, plus kinetic energy initial minus any work done by friction equals final potential energy plus final kinetic energy. All right, so in here, we want to be able to determine the speed of the box when the spring returns to its equilibrium position. Okay, so it's going to start from rest, so that's gone, right? And when it reaches its equilibrium position, there is no potential energy, and there's frictionless, so that's gone. So we have basically potential energy being converted into kinetic energy, and then from here we should be able to solve for V, or give an expression for V. Okay, V equals what? Okay, what's the expression for V? And we'll hit pause. Okay. Uh, okay, 5.52. Okay, 5.52 here is asking us a pendulum of mass m swings on a light string of length L, and it goes back and forth here. It says here if the mass is released from rest at an angle of theta as shown, find the maximum speed of the pendulum as a function of theta, L, and any required fundamental constants. All right, so to help you out here, let's go ahead and do this here. So I'm going to go ahead and kind of draw this here, and we'll go ahead and kind of draw this here. So remember, this is delta, or this is delta y, or this is h right here. This is the delta y here. So this is L, right? And we talked about this side right here. This side here is going to be L cosine of theta, right? That's L cosine of theta. Okay, that's L. All right. So this is L cosine of theta. Let me make it a bigger L here. Okay. And so what we got here is potential energy initial plus any kinetic energy minus work done by friction is equal to final potential energy plus the final kinetic energy. So it says here, find the maximum speed. Okay, so it starts from rest and swings all the way down here. So up here, kinetic energy is 0. So the initial kinetic energy is 0. And down here, the final potential energy is going to be 0. Okay, so we can see here then that this is 0, this is 0, and that's going to be 0. So we have the potential energy for the pendulum here, gravitational, has to equal the kinetic energy here. Okay, so from here, we should be able to solve for V. Okay, what's the expression for V? Okay, and then 5.53, a ball is thrown vertically upwards. Plot the ball's total mechanical energy, kinetic energy, and gravitational potential energy versus time on the same axis. On the same axis. Okay, all right. So what that means is that we're going to go ahead and take a look right here. Okay, and this will be energy here, and we'll go ahead and do this one together. Okay, so plot the ball's total mechanical energy, kinetic energy, and gravitational potential energy versus time on the axis. Okay, so a ball is thrown like this here, it's thrown up and it comes back down. Okay, all right, so what's going to happen is that the energy, so whatever the initial, so when the ball goes up, it's going to have some kinetic energy. Okay, that's going to set the boundary for the total energy. So the total energy is, we'll kind of draw a line like this. That's the total energy of the system. Okay, now we'll go and use a different color. We'll use maybe red for kinetic energy. So that as a ball is thrown up in the air, it begins to lose kinetic energy, transferring to potential. At the very top, it has no kinetic energy. Then on the way back down, it begins to gain kinetic energy. So it should be something kind of like this, kind of a parabola like this here, right? Up like this here, and we'll kind of go like this. All right, so this is going to be kinetic energy. So K is for kinetic energy. Okay, now here, 0 potential energy, but at the very top we have maximum potential energy, and on the way down it loses potential energy to kinetic energy. So we'll go ahead and use blue here. So potential energy should look like this, right? And we'll come on back down like that. Good. Okay, this is a very important graph to look at. Okay, so let's take a look at it, and we see that the total energy is constant. Okay, and this red is kinetic energy here, and this this teal color is going to be potential energy. Okay, gravitational. So when kinetic energy is 0, potential energy is maximum. Okay, when kinetic energy is maximum here and here, potential energy is 0 here and here. Notice that is nonlinear. Okay, this is a nonlinear relationship. Okay, and a couple of reasons why. Well, the main reason is that, let me go ahead and use red here. Kinetic energy, right? Kinetic energy is 1/2 mv squared. So this is a squared term. Okay, it's a squared term. So it's not linear. It's parabolic, or it's quadratic. Okay, um, you go ahead and hit pause. All right, so we'll go ahead and let you work on 5.54. Okay, I'll give you a hint. 3 of these are correct. Okay, 3 are correct. Okay, and let you go ahead and work on 5.55 as well. Okay, and remember now we want to break this into 2 problems. Okay, so give you a hint here. I need to know at this location here, what is V? Once I know that, this becomes a projectile motion problem. Okay, and we should have some familiarity with projectile motion problems. Okay, all right, we'll hit pause. Okay, I'm going to 5.56. I'm going to save this for exam 4. Okay, I'm going to ask this question. This will be one of the free responses. This will be on exam 4. We'll save this and let you think about this here, give you a preview. This will be on exam 4. Okay, all right, so now before I cut you loose here, we want to look at some supplementary problems. Okay, we hit pause. All right, so these are some more AP level type questions. Okay, we want to apply what we learned to this here, and we'll look at this problem in more detail. A box of mass M is released from point A, top of a long frictionless slide. Point A is at height h above the level of points B and C. Okay, so this is point H here. Although the slide is frictionless, the horizontal surface from B to C is not. So there is some friction here. There's friction here. Okay, the coefficient of friction, okay, says here, okay, although the slide is frictionless, the horizontal surface from point B to C is not. The coefficient of friction between the box and the surface mu k and the horizontal distance between points B and C is x. Okay, so this is not frictionless. There's friction here. Okay, find the speed of the box when it is height above point B is 1/2 of h. Okay, so basically at this location here, what is the speed of this box here? Okay, what's v when it's here? Okay, what is v? Okay, good question. All right, so we'll go ahead and do A here, and we'll go ahead and start off with the conservation of energy, initial potential energy, plus the initial kinetic energy, right, is equal to minus any work done by friction is equal to the final potential energy plus the final kinetic energy. All right, so potential energy we're going to start off with is going to be simply mgh, right? There's mgh. Now it starts from rest, so there's no kinetic energy and there's no work done by friction. Okay, equals, now at the bottom here, the potential energy is 0, but there is kinetic energy. There is kinetic energy. Okay, or actually, my bad. Whoa, time out. We want to find out what it is at this position right here. So looking here, we know that there's no kinetic energy and there's no work done by friction. Okay, so when it's at this position here, it's going to have both potential and kinetic energy. All right, so let's take a look here. We're going to have here mgh is right here. Okay, is equal to, okay, so it's going to be mg, and we want to do 1/2 h. So here's 1/2 h is right here. Okay, plus 1/2 mv squared. All right, so from here, you should be able to solve for v. Okay, so we'll hit pause and we'll give you a multiple choice question to solve for v. What does v equal? Okay, we'll hit pause. Okay, all right, so part B here is simply find the speed of the box when it reaches point B. Now there is a shortcut, but we'll ignore the shortcut. Again, we'll start with potential energy initial plus kinetic energy initial minus any work done by friction. It's going to have to equal final potential energy plus the final kinetic energy. All right, so this time we're going to start from here, and what's the velocity right here at point B? Okay, so it's going to start with no kinetic energy, there's no friction, and potential energy is 0 at the bottom. So simply have u square root of or excuse me, potential energy initial is going to equal the kinetic energy. So we should be able to use the appropriate value equation here and solve for V. Okay, we'll hit pause. All right, so C now says determine the value of mu k so that the box comes to rest at point C. So we know what the velocity is here. The box is going to be here. It's going to slide across in this direction. It's going to come to rest at point C. Okay, so what's mu of k? Okay, all right, so basically we can look at the problem from here to here. Okay, now we can do several things here. We can do conservation of energy, or we can also use the work energy theorem. Okay, all right, so let's go ahead and take a look at the work energy theorem. Okay, work energy theorem here. Okay, well, actually, we can go ahead and use conservation of energy. So here's potential energy here plus any kinetic energy, right? Initial minus any work done by friction is going to equal the final potential energy plus kinetic energy. All right, so potential energy is their initial potential energy is 0. There is kinetic energy, okay, based on what the speed was at B. So there is kinetic energy, and we want to find out what's the work done by friction. Now, there's final potential energy is going to be 0, and the final kinetic energy is also going to be 0. Okay, so essentially we have initial kinetic energy is going to equal to the work done by friction. Okay, so this should be 1/2, right? M v squared is going to equal, this is going to be, was it mu kinetic mg, right, mu mg times delta x. So we have everything that we need here to solve for mu k. All right, go ahead and we'll hit pause, let you work on that. All right, so this will be supplemental part B, AP level question here. Okay, so the diagram below shows a roller coaster ride which contains a circular loop of radius r. A car of mass m begins at rest at point A. I'll let you read it here, and it's going all the way down like this and goes all the way around and finally like this. Okay. Um, Okay, so it says here travels on a flat portion of the track from B to F. So this part here has friction. So there is friction here. Okay, there is friction, but this part here is frictionless. Okay, it says here find the centripetal acceleration of the car when it's at point C. Right here, this is point C. Okay, all right. So let's take a look at A here. What is the centripetal acceleration at point C? So if we recall, centripetal acceleration is equal to, was it, it's going to be, I think it's v squared over r, right? Okay. All right. Now, take a look at this problem here. Okay. So we're going to have the box come like this, and it's going to come to this location right here. Okay. So right here. Okay. So we can figure out what's the speed here, or what's v at this location. So we will use the conservation of energy. So potential energy kinetic plus potential energy, kinetic energy initial plus potential energy initial minus any work done by friction is going to equal final kinetic and final potential. Okay, and we'll put the potential here. All right, now as it starts from rest, okay, so that's going to be 0. So there is some potential energy initial, gravitational, and that can be described by mgh. Okay, no work done by friction, so that's gone. Okay, now here it's moving, so at this location it has both kinetic and potential energy, gravitational. So the kinetic energy is going to be 1/2 mv squared, like so. Okay, plus now here it's going to have some potential energy because there's some distance here above the ground, and if this is the radius, c is a distance r from radius distance r from the ground. So this will be mgr, like so. All right, so here's this equation here, and what we need to do is we need to solve for v. So from here we need to get v. Okay, once we get v, we can plug it into here and do some simplification and see what the final result is. All right, we'll let you go ahead and I'll hit pause and let you guys go ahead and work on that. All right, so b, what's the minimum cutoff speed vc that the car must have at point D to make it all the way around the loop? Okay, so this is a normal force problem. So here's the loop here, right? And we'll assume that this point represents all the forces acting on the car at point D. Okay, so we definitely have a force of gravity, which is mg, acting this direction, and we also have the normal force also acting in this direction. And centripetal acceleration is also acting in this direction as well. So all three of these are acting downwards, and we'll go ahead and use that as positive going down. Okay, so here we have some of the forces, right, is equal to mv squared over r, like so. Okay, all right, so here we have the normal force going down, right, plus mg, right, is equal to mv squared over r. Okay, now we do need to solve for v, but we need to solve for v when the normal force is equal to 0. So when normal force is equal to 0, what is v? So v is equal to what? Okay, and we'll go ahead and pause and let you figure that out. All right, so part C, okay, is what is the minimum height h necessary to ensure that the car makes it around the loop? All right, so from part B, we should realize that v was equal to the square root of gr, right? So that was the correct answer for part B. All right, so here we got to figure out what is h in order for this to all, how high do you have to start from so it goes all the way around like so. All right, so again, we'll go ahead and start with kinetic energy initial plus any potential energy initial minus any work done by friction is going to equal the final kinetic energy plus the final potential energy. All right, so starting from rest, that means that's gone. Okay, so our initial height will have your mg, and we'll call it HO for our initial height. Okay, there's no friction, so we'll get rid of that term. So we have mgho. Okay, now at this position here, there is going to be kinetic energy, absolutely. 1/2 mv squared, okay, plus, okay, now here, there's also some potential energy. It's going to be mg. Now the potential energy can be expressed as 2r, okay, because it's 2 times the radius, right, 2r, okay. All right, so if we look closely here, okay, now from here, some things do cancel out, okay. We do have to make a substitution here into here. So I want to get a value for HO is equal to what? Okay, all right, we'll give you a multiple choice to look for and go ahead and work that out, and we'll hit pause. Okay, all right, so part D here. So here's part D, okay. Okay, so what happens if h is 6 times the radius and the coefficient of friction between the car and the flat portion of the track from B to F is zero point 0.5? How far along this flat portion of the track will a car travel before coming to rest at point F? All right, so we'll go ahead and use conservation of energy. So initial potential energy plus initial kinetic energy minus any work done by friction is going to equal final potential energy plus the final kinetic energy. All right, now, so we're going to start from rest, right? So this term is gone, okay? But this time there is friction. Okay, there is friction, so we can't cross this out. Now, on this flat portion here, it's going to come to rest. So if it comes to rest, that means kinetic energy is gone. And plus, this is the flat surface, or it already traveled, so the height is going to be 0. Okay, so that's also going to be 0. So in effect, we have here the potential energy initial is going to equal to the work done by friction. Okay, so what is the initial potential energy? It's going to be mg, and h is what, 6r. So we're going to put 6r here, and that's going to equal mu mg delta x. Okay, all right, so from here, some things cancel out, and we want to solve for delta x. And we have multiple choice answers for that one. We'll go ahead and hit pause and let you work on that. All right, so part C here. A student uses a digital camera and computer to collect the following data about a ball as it slides down a curved, frictionless track. The initial release point is 1.5 meters above the ground. The ball is released from rest. He prints up the following data and then tries to analyze it. Okay, all right. So here we are here. Okay, so based on the data, what are the corresponding heights for each data point? All right, so it starts from rest, velocity is 0. Okay, h is what here? What's the height here? Okay, then at 0.05 seconds, the velocity is now 1.41. What's this height here? Okay, and all the way so on and so forth. That's what we're trying to find. Okay, based on the data, what are the corresponding heights? Well, if it has velocity, that means it has kinetic energy. So potential energy is being converted into kinetic energy. All right, so here's how we might approach A. Okay, so A is right here. Okay, and so we got here is that we have, okay, so we have potential energy initial, right, plus kinetic energy initial, right, minus any work done by friction is going to equal potential energy final plus kinetic energy final. All right, so we do have an initial, so let's go and plug this in. This will be mgho. Okay, and I think this is our initial height. It says 1.5 meters, so this is ho right here. Okay, all right. And so it has no kinetic energy, there's no friction. Okay, however, it is going to be transferred, so this is going to be mg h here, right, plus kinetic energy. Okay, so now in the first one here, time is 0, velocity is 0. Okay, so for our first, so we'll call this the first calculation here. Okay, so this is HO. So okay, we need to solve for H. What is H here? Okay, so in the first situation here, this is 0. Okay, and this is mg, and that's mg. So essentially, HO is equal to H. Okay, so the first height here is just going to be the height, which is, was it 1.5 meters, right? Okay, now take a look at the second point. Then after I do this one here, I think you guys are on your own. Okay, so the next one here, okay, so let's take a quick look here. And let's just see what cancels out and what doesn't cancel out. So here we have mg, here's ho, right? Here's ho, equals mgh. There's h right here, okay? Plus 1/2 mv squared. Okay. All right. So we look closely here. So I want to solve for H here, right? So M's cancel out here. M's are gone. Okay. And there's an M gone here. Okay. So here I have, I'm going to bring this over to the other side. So we'll have here, so this would be GHO, right? GHO minus 1/2 V squared is equal to GH here. Okay, so to solve for H, then here's H. Right, here's H. Looks like okay. If I divide by G over here, I'm just going to have the initial height, okay, minus whatever V squared is divided by 2G, or yeah, 2G. All right, and this is how we would calculate the height. Okay, so go ahead and try it out for the next 4 values there. Okay, then on B here, B is asking what time segment experiences the greatest acceleration and what is the value of this acceleration. Okay, so acceleration is simply just going to be the change in velocity over the change in time. Okay, and see which one of those is the greatest. Okay, and then we'll hit pause, let you work on that one. Okay, now part C here. Here's C. How would the values change if the ball were replaced by an identical ball with double the mass? Okay, how would it affect? Okay, I'll let you answer part C. All right, last one here. Okay, last one. A car with mass 800 kilograms is traveling with initial speed of 10 meters per second when the brakes of the car are applied. The car starts to skid and it experiences a frictional force with mu k of 0.1. Okay, what is the skidding distance of the car? All right, so we'll go ahead and start with initial potential energy plus initial kinetic energy minus any work done by friction, right, is equal to, right, uh, final potential energy plus the final kinetic energy. All right, so now it says here, what's the skidding distance of the car? That means it comes to rest. So when it comes to rest, it'll have no potential energy, it'll have no kinetic energy, all right? And so it does have initial kinetic energy, but there is no potential energy. So basically, it's going to be kinetic energy initial is going to equal to the work done by friction. So from here, we should be able to solve for the skidding distance, which is going to be delta x. All right, so this will be for part A. Okay, and then part B, we'll let you think about this one here. So part B, how would the skidding distance change if the initial speed were doubled? Okay, so just kind of think about that. This would be 1/2 mv squared. Okay, so what happens if I double this? Okay, suppose it was 2v. Okay, and I go like this and I square it. How would that change the outcome here? Okay, we'll leave that for part B. Okay, and then finally, part C here, how would the skidding distance change if the initial mass of the car were doubled? Okay, so here's the kinetic energy, right, is equal to 1/2 mv squared. Again, what happens if it was 2m? How would that affect the outcome? All right, we'll go ahead and hit pause, and that will conclude video 44.